Welcome to the channel Professor Da Vinci. Hello everyone, I am the professor. Subscribe and hit the notification bell to stay updated. Today we are going to see the mathematical intuition of a DES algorithm. The math made simple, exploring the core principles of a DES encryption. Let's start with the block diagram. This is a general block diagram of a DES algorithm. DES is a symmetric key block cipher encryption algorithm widely used for securing a data in the past. It operates on a 64-bit block of data and it employs a 56-bit key, which is expanded into 16 subkeys of 48 bits each. To perform both encryption and decryption, DES applies a series of 16 rounds of substitution, permutation, and bitwise operations using these 48-bit subkeys to transform the plain text into ciphertext. DES involves three major steps. First step is to generate a 16-bit subkey. Second is to encode each 64-bit block of data, and the third swapping and the final permutation. Let's start with step 1, generating 16 subkeys. So in step 1, let us assume the key 64-bit key, so 110011, like that. So for our easy understanding, this 64-bit key length is given in the table. First bit number, on the second bit the bit 1, third bit 0. From here 1100, same thing 1100, and so on. In this we need to eliminate 8 bits because from the 64-bit key we need to reduce it to 56-bit. So every eighth position of the bit is discarded. So total we have a 64-bit key, and minus 8 we yield 56-bit. So every 8 bit is discarded. For example, here the 8th bit 1, so this is the one, the 8th bit 1 is discarded, and the 16th bit is 0 is discarded, and the 16th bit 0 is discarded, and so on. So once we reduce the bit 64 bits to 56 bits, now we need to perform the permutation, first permutation. So we have the permutation mapping, so we can say this is a permutation chart or permutation table 1. So in this we are going to map 57th bit 0. So where's the 57th bit? This is the one. This is 64, 60, and this is the one, 67, 69, 68, 67. This is the 67th bit 0. Same way 49th bit, 41st bit, like that we need to get the bit from the key. Let us say 4th bit is 0, so here is the 4th bit is 0. So like that we need to populate the PC1. Once we populate the PC1 table of the bits from the K, that is the key, so this permutation is made for jumbling or shuffling the bits. Once we make this one, then rearrange. Again you need to collect from here 0 0 0 0, so we need to collect from left to right, collect row wise. So whatever the resulting bits got from the permutation table 1, it is termed as a K plus. So this K plus has 56-bit key. The next step is to split this key into left and right half, say C0, under D0, where each half has 28 bits. So 56 bit divided by 2, because we are going to split into two halves, so it will yield 28 bits. So the first half, 8, 16, 24, this is the first half of K plus, and the second half of the K plus. This is C0, and this is and D0. Now we need to perform the left circular shift 16 times, because we need to get 16 subkeys, right? So we need to perform a left shift based on the table given here. First iteration, second iteration, 9th iteration, 16th iteration, we need to perform 1 bit circular left shift, and the rest of the iteration we need to perform 2 bit. For example, let us take from C0 and D0 circular shift. So this 0, first one, this 0 comes here, and this one comes here, the first one comes here. So we yield C1. This is the result of the first iteration, that is shifting a left shift of 1 bit. So this is 0 comes here, and this is the last, this 1 comes here. So this is the first one. In second iteration, from this C1 and D1 we need to perform again one time 1 bit. So this 0 comes here, so that's why we have here 2 bits, 0 0, and this one here comes here 1 0. So this is the second iteration. The third iteration, 2 bit circular shift, as seen in the table. The first iteration, second iteration, 9, 16 is a 1 bit circular left circular shift, and the rest of the iterations are 2 bit circular shift. So based on that we yield all the iteration results until C16 and D16. So this is the subkeys of 16. For 16 rounds we got 16 subkeys. Now we need to generate the subkeys with the permutation table too. So here what we are going to do, we are going to concatenate these two things, C1 and D1, join together. So C1 and D1 joined, so like that we are joining all the halves into a single 48 bit length. After joining, we need to use the permutation chart or permutation table too. So from these, say C1 D1, we need to take the 14th bit, put in the 14th column, 14th cell, 17th bit, 11th bit, like that, and so on. We need to extract the bit from this C1 and D1 and put it in the permutation table as specified. So the first, and you need to collect everything from left to right, so we will get K1 of 48 bit length. Similarly, you need to perform this permutation table chart for all those combinations of C and D 16 times. We will yield the 16 shuffled 48 bit keys. 64 bit. So in short, we can say 64 bit is given to PC1 to make 56 bit length, and then PC2 to make 48 bit length. So now we got the perfect 48 bit length subkeys, 16 subkeys. So this is the step 1. Now going for the step 2. Encode each 64 bit of block of data. So assume that we have the message M. This is the data, 64 bit data. So encode each 64-bit block of data with the initial permutation. Similarly, as we did, we have the standard permutation table. Initial permutation said we can say this is IP. Extract the bits from this message and put it in the respective cell, and then we yield the initial permutation result. Next, divide the permuted block into two halves, left half and the right half. So again, from the message we are going to split into two halves. So left half and the right half, 0 0 1 1 0 0, so and so on. So we get the messages now is a permuted result of the message. We get L0 and R0. As we see here in the block diagram, so the 64-bit message goes to the permutation. After permutation, we are splitting it to 32-bit half of left hand side and 32-bit for the right hand side. The same thing is happening here. Same thing we have done here. So we are splitting and we got the left half and the right half. Then we need to perform the functions. So L1, so as see in the figure, this L1 equals Rn minus 1. And what is the, so whatever the L1, it will be got from the previous step right. See, previous step right, we got the same thing as the L. And to perform right, we need to perform the series of mathematics to perform the right side. So L1 equals the previous R0. And what is the R1? R1, we need to perform some mathematics on L0. So for round 1, L1 equals R1 minus 1. R1 equals L1 minus 1 plus a function of R1 minus 1 comma K1. So L1 equals R0. So already we have L0 and R0 from the previous operation. We have L0 and R0, which is the result of the first permutation. So we got the L0, I mean L1. So L1 is the same as a R0. Now we need to find R1. So R1 is a function of R0 comma K1 and XOR with the L0. To calculate F, we first expand each block R0 from 32-bit to 48 bits. This is done by using selection table that repeats some of the bits in R0. We will call the use of this section table as a E. This E of R0 has 32-bit input block and a 42-bit output block. So we need to expand the 32-bit to 48-bit, because from this 48-bit of message we need to perform the operation with the 48-bit subkeys. So that's why to perform the mathematical operation of 48-bit subkeys, we are converting the plain text of a 32-bit to 48-bit by repeating some of the bits here. For example, this is the R0 E bits selection table. Here if you can see that 1 and 1 is repeated again. The first bit is repeated again, and if you see some of the bits are repeated again and again. See here 12th bit is repeated. So we are converting a 32-bit to 48-bit. So by repeating some of the bits again and again. So with this one, with this selection table, populate the table. See 32-bit. So the first is 0 here. So populate the bits from left to right, and finally you collect it everything from left to right. So we yield the 48-bit message. Next, in the F calculation, we XOR the output with the key K1. So next step, what we need to do, already we have the key, subkey. So with this subkey, we need to perform the XOR operation with this E of R0. And finally, we yield this one. So 1 XOR with a 0, 1. 0 XOR with a 0, 0. And so on. The result is 48-bit, or we can say 8 group of 6 bits. So this is a 48-bit. So now we have to divide into 8 groups of 6 bits each. So here we are going to divide this one, 8 groups of 6 bit each. So each group is termed as a B1, B2, B3, B4 and so on. For example, the first 6 bits, sorry, this is a little aparted. So this is the first 6 bit, 100, 100, 100. So what we need to do, take the first and last bit. What is the first and last bit? The 1 and the 0. This is the first bit and the last bit, 10. 10 is equivalent to 2 decimal. I mean 10 binary is equivalent to decimal number 2. And the middle, what is the middle one? 0010. 0010 also corresponds to the equivalent decimal number is 2. Now we need to, from this 2 and 2, we need to find the value from the S box. So to second row and second column, we got 14. Convert the 14 decimal to binary. So we will get 1110. So this is the S1 of B1. Similarly, perform the same step for all B1, B2, B3 until B8. So we yield this. We yield this. This is the S box output. Once we get the S box output, now we need to perform the function. F is the F permutation. So from the result of a S box, again we need to perform the F permutation. Again these bits are shuffled here and corrected as said in the previous. So we yield the F of R0, K1. Then finding the output of round 1. So still we are calculating. So we got a function of R0, K1. We have a L0 and R0. Now we need to compute. For n equal to 1, we have L1 equals R0. Already we know that. Now we are going to find the R1. R1 is the XOR operation of L0 and the function of R0 and K1. That function is what? That is a F permutation. So doing the XOR operation, we yield R0, R1 and the L1. So this is the output of the round 1. Round 1. Similarly, you repeat the same step for 15 times using the key subkey of already we are using K1. Then you need to use F of R1, K2. Like that, you need to perform the same operation for 15 more times. Once you perform 15 more times, finally we yield L1, L16 and R16. Now we reverse the order of these two blocks to apply the final permutation. So instead of having L1, L16, R16, we are going to swap. That is the final step. So first put the right hand side, then left hand side. Just you need to concatenate both the strings. So 10011 is the first one, and then followed by the 1101 L16, 1101 followed by round 16. After swapping, do the final permutation. Use the table from this, extract the 48th bit, 8th bit, 49th bit, and put it in the table, and finally collect it from the left to right. So finally we get this one. Once you get this, the output of the final permutation, convert this to hexa. We get the ciphertext, hexadecimal ciphertext. So this is how the DES algorithm works. Remember to subscribe to Professor Da Vinci for more tech and cybersecurity insights. Like and share this video to help others understand. Thank you for joining us today. If you have any questions or ideas for future videos, please drop them in the comment below. Stay safe and stay curious.